Well, I guess I'll get started. I have some pretty dense material, I guess, to cover. First things first, I am at the IBM Spark Technology Center, and here's a lovely picture of what that office looks like. It's a couple blocks away from here. We have some very pretty growing plants on the wall. They're alive, so you should stop by and take a look at them. A little bit about me. So this is all the many, many schools I've went to. I've been primarily in academia. I've been in IBM for about 2 years now, so doing new research on supervised learning and learning about Spark and moving into this new space. But the main agenda is why we're here. So why do we need online semi-supervised learning? So these are some of the use cases that are predominant in this kind of area. So we have malware and fraud detection on things like smartphones. So you want to have real-time detection in those cases. You want to have it be online, and you want to have it have an adaptable model in those cases because you're not guaranteed to have the same malware invading all the time. Obviously, viruses change pretty rapidly, and your model needs to be able to adjust rapidly. We have real-time diagnosis in medical and health fields. We also have NLP and speech recognition, which is another thing. For instance, when you talk to Siri or any of your kind of audio processing applications, this is what would do that. And one of my favorites is real-time visual processing. So a lot of the previous talks I've given have been on autonomous vehicles and having frameworks in the autonomous vehicle space. And you can use this kind of learning online and semi-supervised in this case where you have some unlabeled data. The case we're going to look at today is obviously, well, not obviously, but is the stock market data. We're looking at Nasdaq, and we're going to examine how we can look at stock predictions using unsupervised and online learning. So why online learning? So we just kind of went over some of the cases, but some of the constraints that we deal with are, we have incremental and sequential learning for real-time use cases, such as time series data. That is usually what you have in situations like Nasdaq. We need to predict and learn from the newest data, and we need to optimize for low latency in real-time cases, meaning you don't want a response that takes minutes when you're in a real-time situation, and you need the processing within seconds. And so often this is used in conjunction with streaming data. Also, what happens a lot in the online cases is that some of the older data may be disregarded because they're not necessarily guaranteed to have consistency across models over time. But this is something we'll look at when we examine the framework a little bit more deeply in the coming slides. So some of the constraints of semi-supervised learning are you have smaller training sets. You have less labeled data initially. So this is one of the underlying assumptions in semi-supervised learning, is that your labeled data set may not be as large as you would necessarily like for a fully supervised task. And there's classifying or predicting this unlabeled data. How do you do that in a timely fashion with the lowest possible error? And then there's understanding the underlying distribution. So you can have mixed, like Gaussian mixtures or like different mixtures happening at the same time, but you're not necessarily guaranteed to know what the distribution is that underlies your predictions. So inferring the hypothesis is a little bit harder than it would be in a fully supervised case. How do we bring these ideas together? So the first thing is we want to acquire a sufficient ratio of training data. So batch learning is much slower and more difficult to update. It's more difficult to update a model. That's one of the constraints in having a purely batch implementation of this. And there's also maintaining accuracy. So you have to retrain if you're going to maintain accuracy over things like concept drift or catastrophic events. And in order to do that efficiently, you cannot rely on a large batch set, not if you want to use it in a real-time and online case. And then you want to make sure you're meeting those latency requirements. So what we have is a hybrid online and semi-supervised learning framework that we developed. It's a variant of the Valpol-Babbitt methodology, which I've linked the paper there, which is John Langford out of Harvard, does some very pivotal machine learning research. And this is kind of an overview of what the general framework looks like. Some of the, I guess, features of this is that you can deal with an abundance of unlabeled data. You can have real-time learning in the IoT setting, which is something that I've been working on for, I guess, the past year or so. You can have semi-supervised learning that can improve predictions. I think that's counterintuitive with a lot of people. They don't think that having this unlabeled data in the data set is going to help, but actually, empirically, we have seen improvements on classifications and predictions when including unlabeled data, sorry. We also need to address the challenges of incremental learning, optimizing for low latency, and the hybrid framework, I think, does all of these things very well. So in the traditional sense, you start off with your supervised learning over a batch where you're trying to minimize some loss function or some optimization function if you're looking at a utility function over the entire batch. In the online sense, you're looking at a portion of all of the data. So you have n instances and you're looking at 1 over n of the loss function that you can derive for that particular instance. In distributed learning over this mini batch, you have M nodes doing processes of n instances each in a streaming format, and each node is processing some subset of the initial batch of data. And in a streaming batch, depending on how fast that's coming in, it can be very, very small or it can be much larger. For instance, if you're dealing with real-time stock data, you can get data in the milliseconds. So maybe a batch might have 100 or 1,000 instances, whereas in something slower where you're doing maybe a medical diagnosis, maybe your batches only come in at like 10 every second or so, and then you have maybe 2 or 3 instances in each node processing. But that's something we'll also look at. So this is a little bit formal definition of how we think about semi-supervised learning in the general case. So this is kind of the general theory behind it. If you want to read all that. Basically, we're trying to create a new training set where we take a labeled and unlabeled data set and combine them. But we can't combine them willy-nilly. We need to combine them in a meaningful way that makes sense for our data, makes sense for our prediction, and makes sense for what we're trying to optimize for. So this is kind of an overview of what the framework will do. So we have this labeled data, and we're working with the assumption that the labeled data is a smaller set because that's just the general theoretical underlying assumption in semi-supervised learning. And we have a much larger unlabeled data set. And we want to combine these into an initial training set and then use these to infer a model. And then we have, additionally, our online streaming data, or labeled and unlabeled data coming in. So if you're working with stock data, you may have some data that comes in labeled, and you may have some data, probably the vast majority of your data, that comes in unlabeled. So you don't necessarily know how a stock performs the same millisecond that it's reported, but you may know 5 seconds later. So you actually need to have an update feature for updating the data that you've already labeled, and also making sure that the predictions that you've made on the unlabeled data are correct. So we have several policies for dealing with this kind of bringing together of the L and U data sets. So this is kind of a more detailed look at our the batch component of our framework. So this is the out-of-core component. This is not the part that runs in memory. We have another all-reduced component that runs in memory and gives you your real-time predictions in like one online pass. This is where you put the data after you have a training data set and after you've have gone through the amending policies to make sure that you're adding data from both the labeled and unlabeled data sets to your batch correctly. And then you're allowed to get new updated models from this. You can also have multiple learning modules in the batch from M1 to MN. And you can have a retrain policy, there's an active learning policy, and some custom parameters that we'll look at a little bit more in the coming slides. So with multiple model learning, so we have M1 through MN, and with co-training, we have expandable learning modules, multiple learning algorithms, meaning you can put in multiple algorithms into the same batch mode and do a comparative analysis and try to figure out which are your high confidence and which are your low confidence predictions and how to add those into your batch data set correctly. You can also do something like called co-training for high dimensionality data sets, and it improves the confidence. So co-training involves a feature split and then training different models on the different views or perspectives of those features and seeing if you can get agreement on the two models. It accounts for different biases across learning techniques, improves confidence estimates in practice. So this is not just theory. In practice, you actually see improvements in the predictions that you generate using these different multiple learning methods or ensemble methods. And then it reduces variance and helps to avoid overfitting in your data, which if you're dealing with time series data for a given window, you could definitely have some overfitting, and then in the next day, maybe your stocks take a hit because of something that happened in one of the markets, and you have to change your underlying model. So you need to have something that's responsive enough to account for this. And I think the multiple module learning definitely improves that performance. And so one of the things that we do with the multiple modules is model averaging. So you can use something called a committee method, and the multiple models can be used to regularize weights in our online implementation. It can judge the confidence of a predicted label by taking the posterior probabilities over the normalized distribution or over whatever distribution you've defined. If you're doing a discriminant function, then you can also use something of that nature, and you can calculate your confidence, and then you can check the agreement between the different models. The likelihood of that agreement can be used to determine if the prediction is high confidence or low confidence. And then you can have the amending policy make sure that you only allow high confidence predictions into your batch learning set. So this is kind of an overview of the amending policy and what happens with high and low confidence predictions. And this is kind of a cute funnel that I made that has the unlabeled low confidence data and the labeled data, and then making sure that you strain it or have it reviewed or filtered, I guess, through the amending policy so that your training batch is, has a distribution that you can understand and makes predictions that are the most accurate. So let's say you do all this and at some point you decide, even now my predictions are not good, what do I do? Well, you can have a retrain policy, and the retrain policy can be based on several different factors, including loss minimization, the accuracy, if you have increasing or decreasing accuracy, is your loss actually minimized, or are you actually seeing an increase? You can have scheduled, meaning you have a large batch, it's out of core, you want to retrain it on some interval, maybe a 24 to 48 hour interval, depending on how large your batch is and how long it takes to process. And then some further optimizations would be limiting it to a window. So maybe you want to retrain the batch, but only on data that happened within the last 30 days, because right before there was a market crash, and that data is a catastrophic event that you can't use or don't want to use in your everyday day-to-day model. Another thing you can do is have subsampling over very large data sets that can improve the batch processing speed. So if you have a very large data set and you don't want to necessarily run the whole batch, but you do want to see sort of how it works over time, you can do something like a 1 in 3 subsample or a random subsample, depending on if it's time series data or not, to verify the accuracy. So given all that, what happens to low confidence predictions? So with low confidence predictions, we have an active learning policy. So you separate data set holds these instances. So when you have an instance that has a low confidence level on it, you can isolate that instance and say, can you query a human or an oracle on what this data represents? So if you have a time delay in when you're going to get in those labels, you can say, query the oracle, do we have labeled data for this instance yet? If not, then I need to query a human because I'm still uncertain. And I think in general with all kind of AI infrastructures and machine learning infrastructures, this is still the case. So Google has over 10,000 contractors performing this function right now. And they're vast farms that Facebook is hiring 3,000 new content monitors for the job AI cannot do. And Netflix and Amazon are both bringing in humans to improve the CTR recommendations. So ultimately, you can get recommendations, you can get tone analysis. Let's say you want to figure out how something feels, whether it's angry or sad. But unless you have humans on the other side of that verifying things like emotions, it's very hard to have accurate or highly accurate labels. So you do need a separate validation, which is the active learning policy that we have here in this framework. These are some of the custom parameters like window size, amending times, loss threshold, accuracy threshold, and subsampling that you can implement in the framework to kind of change how the data is being processed and optimize for what works best for your cluster or your server system within your particular space. And then the next we go into the all-reduced component. So the all-reduced component is the online component that handles things in one online pass, and it's based on, again, the TerraScale learning paper with John Langford. And it's a very standard implementation of multi-nodes over stochastic gradient descent, or LBFGS, where you have your instances divided over the number of nodes in your cluster, and each one is running an optimization or a learning algorithm and returning the optimum weights and the loss for its particular batch. And this is a subdivision of the entire streaming batch. So again, if you get 100 instances in your streaming batch every second, then each of these nodes would have some subdivision of those 100 instances, and they would process it, return the weights, and return an optimal loss, and then they would have that summed up the tree, and then the best or the summation value of that average would go into the top node, and that would inform your online prediction process. So this is what you have running for your real-time responses, because obviously you don't want this happening with a batch response because you're going to have a much slower return. And so the part that does the caches the models is we have what's called basically a model or retraining cache that has both your local optima and your global optima. And for both of these optima, they're coming from your batch. So your batch is actually returning all of its best weights and its best loss parameters, and your local all reduced component is doing the same thing. And so these things are being monitored consistently throughout the application. And they don't require much room because we're not doing full model switching here, so the caches actually only contain the weights for the different algorithms. So it's a little bit easier to maintain this in memory and have a very fast response time and easy switching time for those weights when you need to retrain. So if you have a retraining policy and you want to retrain on something that you want, I guess, instantly done, you can actually query the cache and pull out the best weights that you have for a local or global and say, implement these now without waiting for the retrain to happen as you need it. So I think this is a very flexible response parameter so that you don't have to have these delays when you switch out the weights or when you retrain your model. But you do have the option, you do have the option of keeping the retraining policy in the monitor, which we'll look at in a second. So yeah, and this is just basically the cache policy. And so in the monitor, you actually have your online predictions running in real time. This is where you're querying to get your responses. This is where Kafka is pushing the messages in for the streaming. This is where the streaming data is processed, pushed out to the all reduce and to the batch, where they handle their separate policies on how to train those instances. And it's also where if we see a degradation in the model that's running in the monitor, we can query the cache and have it retrained. So that's, those are kind of the two options of kind of implementing this in the monitor. So we have the real-time prediction policy with only local latency when initiated. So it's very low latency, stable predictions. Significant changes in weight since last pass can happen if you are not, if your retrain policy isn't aggressive enough. And you have loss minimization and accuracy thresholds that you can set. And then you have the all reduced weights that happen after one online pass, which have lower latency, greater sensitivity, meaning that if something dramatic happens between each set of instances that come in your streaming batch, your all reduced is going to respond to that in one pass, whereas the one that's running in the monitor may take several passes before it updates. So you can kind of set these policies into which category you want to use and which one you want to optimize for. And so we went into looking at this on Nasdaq Data, and one of the things that we use is IBM's data science experience. So I loaded this into the IBM DSX, which we have a booth downstairs. You can look at this in real life. But this is what the code for that looks like. And so this is kind of a data science front-end way of looking at this whole process. This is where I loaded in the jars for this, and then we ran the regression and looked at how it performed. So I think I said before that it's kind of counterintuitive that you get better performance from unlabeled data, but this is a graph of what that looks like. And so just to give you some more objective data, this is coming from a CMU talk where they were looking at HTML documents. And there was co-training run on these HTML documents, and then they had 1,000 unlabeled and then no unlabeled. And the lower line, for accuracy here, so we're looking at accuracy, is actually the labeled documents. The unlabeled documents are actually the taller line, and they actually perform better than expected. And so this happens not just in this case, but over multiple cases that I've listed on the side there. So for our particular case, we looked at Nasdaq data. So these are daily stock market values since 1971. We have about 50,000 instances of this data. One of the excerpts of the features are we have date open, high, low, close, volume, and adjusted close. So this is not the ticker data that comes in, but this is kind of your daily stock market went up or stock market went down kind of thing. We looked at two cases. We did tenfold cross-validation. We looked at regression in both cases, linear and logistic. And these are the results from the linear regression. So this is empirical risk management, where we're kind of looking at what actually performs better when we test it. So if you look at the very thick blue line, which I hope shows up well here, I'm not sure, but the thick blue line represents a fully supervised data set. But if you look at it, you notice it's not the best performer. So the blue line that has a very low performance here at the 3 mark, but then you see like it's still not the best performer overall. So as you move from left to right, you can see that it varies, and that surprisingly, and this is, I'm sorry, looking at different ratios of unlabeled to labeled data. So you have a 10, a 20, a 30, and a 50% of unlabeled data in all of these cases. And we move from left to right, and we can see the performance over each set as we go along. And then the graph on the right represents the average. So we do see an increase in the error on average. So this is the average RMSD on the right. But if it's on the third significant figure, so it's after the decimal point. So it's actually a very small increase in the error, and that doesn't necessarily mean that it's the best performance. So one of the things that I have to mention, the caveat in this, is that I extracted raw data. I didn't do any feature hashing. There was no optimization of the features that were used. There was no initial performance management for the data as it came in. So this is performance on raw data. So given that this is raw data, and given that there were very little optimization done, to see that we still have unsupervised sets performing better, I think is remarkable. And so this is the linear regression case. The classification was even better. So traditionally, unsupervised tasks are, kind of geared towards classification. So going into kind of the continuous or the, non-discrete spectrum of data is a little bit off. But classification, it performed even better. So these are accuracy that you can see. So again, the dark blue line or the thick blue line is the fully supervised set and the accuracy that you see on the fully supervised set. But if you look at the red line, that's 10% unlabeled data, you see that it outperforms the fully supervised set. And then if you go from left to right, you can see that at 30% unlabeled data, we have at least around the same amount of performance as a supervised set. And then 50%, there is a marked decrease in accuracy for 50%, and that would be the green line. But the purple line, again, and then the orange line, which are the 20 and 30% data sets of unlabeled data, are still valid, good performances. I think they are comparable, at least, to fully supervised tasks. So I think it's counterintuitive, but I think it speaks a lot to the way the world really works. So in reality, you don't get a lot of labeled data. People don't give you a bunch of nicely labeled data to process for them and then return it when it's convenient for you. In reality, if you're dealing with real-time cases, you're looking at this data, you're processing it, you may or may not get a label, and you want to have the most accurate prediction that you can. And I think this shows that you can still maintain accuracy over unlabeled data sets for a large ratio of unlabeled data. So I didn't test larger than 50%, and I haven't seen many tests larger than that. So I think the assumption is around 50 to 60% would be kind of a threshold for the unlabeled to labeled, because at some point you should have additional labeled data. So don't give up on labeled data completely. There was also a marked decrease in accuracy around the 30% unlabeled for the log, or for the average log accuracy. So this is logistic regression, where we're kind of just saying, did the stock decrease or increase? And so we're kind of showing the output of that prediction. So I'm not sure what happened for the average there, but again, these are not large or dramatic differences. So they're, again, to the second or third significant figure after the decimal point. So it's kind of, you have to kind of keep that in perspective. Like, it's not what would be significant enough for you to not use an algorithm that is semi-supervised. It's significant enough for you to say, well, I have some tiny, tiny bit of doubt, but this is still a reasonable assumption of the prediction. And so those are kind of the performance things. So some of the future work, and this is a picture of my robot who I usually work with and who usually travels with me but is not here today, is looking at some more complex real-time data sets, looking at real-time streaming and semi-supervised learning for autonomous vehicles. So one of the really cool ways to use this is on visual data and doing things like, I think in the first or second or so slide, we have a picture of a road and trying to distinguish what is a road, what is not a road. And it seems like an easy problem, but actually if you don't have markers like the white and yellow lines, it's actually very difficult to make those distinctions in a real-time situation. And we've seen that if you go outside of into a rural area or any area that is like non-standard, very big city like San Francisco, or I guess small, dense city like San Francisco, and then actually implementing this into a full framework. So all of this work is part of making a fully online framework for an autonomous vehicle that we are testing on the robot there. His name is PQ, by the way. So some additional future work is improving the batch retraining policy to incorporate more information about the distributions of data. So in this initial version, I don't make very many or very limited assumptions about the distribution, because in a real-time setting, you may or may not know very much about an underlying distribution. But I think with like stock data, there are some underlying distributions that you can make some assumptions on and build from, and not just use discriminant analyses or predictions. And then I want to investigate a kind of model switching versus retraining. Like, do we see a significant enough improvement in performance to account for the latency that you would incur with model switching? And how do we minimize that latency? Adding boosting mechanisms in batch for when we have very small training sets. So in here we're assuming kind of a medium-sized training set, but if you have a very, very small labeled training set, how do we boost that and kind of bootstrap those data sets more efficiently? Adding feature extraction for high dimensionality data. So this is obviously kind of a hybrid situation that was devised for kind of high dimensionality data and to kind of address the cursive dimensionality. So we want to basically investigate that further. And then an expansion of Spark streaming ML algorithms. And these are some of the references for this talk. So we had some very cool people doing some very cool research. And if you want to read more about it, I would advise you to take a look at some of these articles and books.
Yeah, let's give her a hand. Great, we have a couple minutes for questions. If anybody has a question, just walk up to one of the microphones. One One thing quickly that I was wondering, if you jumped back to the training set that you're using, it was like 50,000 examples of open and closed, et cetera, et cetera. How are you incorporating like the semi-supervised learning in there? Like, would you remove some of those labels effectively,
yeah.
and then you'd make predictions, like you'd make a prediction on that given label at predict? I guess how are you incorporating that?
So yeah, for the we had initially about 50,000 instances. So I basically did tenfold validation. So for one of the sets, I just remove the labels, and then I posit labels for that set, and then you incorporate those predicted labels into your training set. So that's kind of how you incorporate both of those data sets together. Your predictions may or may not be correct, but it doesn't, I think because you're working with an underlying distribution and you're working with some assumptions about that distribution when you create the model, it doesn't affect the overall prediction rate for the new data coming in. So then after you do the validations, you actually looked at a separate data set that I brought in from newer stock data and ran the test again on the unseen data. So this was not in the training set at all.
Gotcha. So the big conclusion there is that empirically, even though you're using potentially wrong data, it's just not that big of a deal because it still overall improves the predictions.
I mean, that sounds like a big assumption. Like, I wouldn't call it wrong. I would call it less accurate than expected, but yes.
Less, more perfect.
Yeah.
Could you give us an idea of the end-to-end latency and the amounts of data for the inference step?
For which step?
The last prediction step.
Okay, so the overall latency, so I throttled these predictions at 500 milliseconds, which is about half a second for each Nasdaq submission to the streaming. Within that time, you can get a batch of about 10, and then the response rates were less than a second. So I would say between 300 and 600 milliseconds or less. You know, depending on how big your clusters are, the location of your clusters, the co-location, and things of that nature. On this one, we ran it on a local cluster, and so the communication between the cluster nodes is C++ socket-based. So this is kind of underlying the Hadoop infrastructure, so you don't incur the additional JVM overhead that you would necessarily incur with building it all on top of this full stack.
When you say 10 updates, those are 10 ticker updates for the stocks?
That's like one streaming batch. So yeah, okay.
I'm curious if the models are updated per batch, or how often is the model updated in this whole system? 'Cause
Okay, so yeah, so that would fall under the retraining policy. So the retraining policy it's flexible, right? So you're kind of optimizing for your particular use case. But on the batch, that's going to be scheduled, and that's going to happen probably whenever there's a decrease in accuracy or whatever policy you set. On the online pass, you're going to get new weights every single online pass. So every streaming batch, you're going to have new weights, and we're going to add those to local cache. And then you have the option of either implementing those in the monitor or not implementing the monitor and waiting until you actually see a degradation in performance before you implement it.
All right, I think with that, let's give her another round of applause. That was awesome.